Time domain analysis part 2.1. Okay, in this video you will learn on the unit impulse response. So a review from previous lecture. So when you want to find out the system output for t is more or equal than 0, you have to find out by two independent causes. So the first one is the zero input response, and the second one is zero state response. So unit impulse is defined as the limit of a Gaussian pulse. So what is a Gaussian pulse? So an example of a Gaussian pulse is illustrated in figure on the left hand side. So this is a Gaussian pulse, and the figure on the right hand side is showing you the unit impulse. So it is denoted by this signal, this symbol, and the arrow occurring only at that time. So if you multiply an arbitrary waveform xt, okay, this is the input signal xt, with an impulse signal that is occurring at time tau, you will obtain an impulse that have an area of x tau. Okay, so we can view the impulse as sampling xt at time when it is equal to tau. So you will have this equation. So xt, which is the input signal, times with the impulse, which is occurring at time tau, and this will give you an output of x tau times with impulse occurring at time tau. So if you see this figure over here, this is a sampling property of the unit impulse. So this is the impulse occurring at time tau. So the impulse is occurring at time tau. And then you have in figure B, this is the input signal xt, so any signal, and then it will yield an output in figure C. So this is actually the combination of the input signal xt times with the impulse signal occurring at time tau. So your output is going to be an impulse. So any signal that multiplies with an impulse, it will become an impulse occurring at that time, given time. So here, in this case, it is at time tau. So the impulse response. The response of a linear time invariant continuous system to a unit impulse is called the system impulse response, and it is denoted by ht. So you will have an input signal coming into a system. So if it is a unit impulse, so any signal that comes into the system which is a unit impulse, it will yield an output which is denoted by ht, impulse response, sorry. So the output signal will become an impulse response which is denoted by ht. So why is it that the impulse response is very important? Okay, this is the reason. Okay, the zero state response assumes that the system is in rest state, meaning that all the internal system variables are 0. So when you derive and understand zero state response, it depends on knowing the impulse response ht to a system. So any input xt can be broken into many narrow rectangular pulses. So each pulse produces a system response. So if you see this figure over here, you will have a signal like this. So this signal, this input signal of xt, can actually be broken into many narrow rectangular pulses. So you have this one pulse over here, second pulse, third pulse, and so on. Now, since the system is linear anti-invariant, the system responds to xt, which is the sum of its response to all the impulse components. So you have to sum up all this impulse component. Okay, we now consider how to determine the system response yt to an input xt when the system is in zero state. So you define a pulse like this over here. So this figure is showing you a pulse of pt, unit height. So you have the unit height here is equal to pt, and the width is equal to delta t. So this is an impulse, okay, occurring at time is equal to 0. So that's the input. It will yield an output ht that will start also at 0. So this is the output. So the second figure is showing you that the impulse is occurring when your t is equal to n delta t. So that's why your impulse here is t minus n delta tau. And then this one will give you an output which also occurs when it is equal to n delta tau. So it will start here. This is the general equation of the input and output of the impulse. So you have an impulse over here, which is at n delta tau, that is the incoming signal, times with the impulse occurring at t minus n delta tau. And this will give you an output yt, which is the signal that happens at n delta tau. So here you will have an output of the impulse, which is the impulse response. So it is denoted by h. So h t minus n delta tau. So knowing ht, we can determine the response yt to any input at t. Okay. Observe the all-pervasive nature of the system characteristic mode, which determine the impulse response of the system. So you have the incoming signal as t coming into the system, which is an impulse system, and it will give you the yt. So yt is equal to the integration from minus infinity to infinity of at tau, the input signal, times with the impulse response ht minus tau, because it is occurring at time when time is equal to tau, delta tau. Now, how are you going to determine the unit impulse response ht? So usually the question we ask you to find out what the unit impulse for the given equation. So one extra step that you have to do for unit impulse response is that you have to apply the impulse response ht, which is given by this red box over here. So there is one extra step that you have to add in order to find out what the unit impulse is. And then the constants Ci are determined by the following initial conditions. So you have to find out the initial conditions, two initial conditions. The first one is when y not is equal to 0, and then the other one is when your derivation of y0 is equal to 1. So let us see this first example. So find the unit impulse response of a system specified by this equation. So you have d squared plus 4d plus 3yt equal to d plus 5xt. So how do you solve this? As usual, you have to find out what the lambdas are. So that is the first step. Okay. find out what the lambdas are. So you have d squared plus 4d plus 3, that is equal to lambda squared plus 4 lambda plus 3. Next, you have to factorize this, and you will have lambda plus 1 and lambda plus 3 is equal to 0. So that is the 0 input response. So the characteristic mode is equal to lambda 1 is equal to minus 1, lambda 2 is equal to minus 3. So you will have exponent minus t and exponent minus 3t. So y naught t is equal to C1 exponent lambda 1t. So lambda 1t is now minus t, plus C2 exponent lambda 2. Lambda 2 is minus 3t. After that, differentiate your y naught t. So you will have y naught dot t is equal to minus C1 exponent minus t minus 3C2 exponent minus 3t. Next, we have to find out what the C1 and C2 are. So you have to set your t is equal to 0 and substitute y naught is equal to 0 and y dot 0 is equal to 1. So you will have two equations, which is these two. And solving these two equations together, you will have C1 is equal to half and C2 is equal to minus half. So just plug these two values into your equation and you will have y naught t is equal to half times exponent minus t minus exponent minus 3t. Okay, one extra step for finding out the unit impulse response is that you have to find out what ht is. So in slide 13, I have highlighted. We are going to find out the impulse response using this equation. So now you have PD times y naught t ut. So what is your PD? PD is actually this one, your input. So d plus 5. So you will have d plus 5 times y naught t times ut. So what is d? D is actually the differentiation of y naught t. So differentiate your y naught t plus 5 y naught t times ut. So that's why you have this equation here. And finally, when you solve all this, you're going to have the final equation, which is equal to 2 exponent minus t minus exponent minus 3t times ut.